Okay, well, we are back with the fourth of our transformations, and this one being a dilation. This is the only one of the four that is not a rigid motion. Remember, a rigid motion maintains congruence. So a translation, a reflection, and a rotation maintain congruence. A dilation, however, does not. This dilation does affect the size of the figure. It does not change the shape, but it does affect the size. So let's jump right into it. Now, as I have with these other transformations, I've directed all my students to a video by Mashup Math. Again, because of the way they animate it, it provides a little bit better understanding conceptually than we can provide on a static screen, the board or the screen here with their video editing. I think they do a pretty decent job of keeping it simple, but yet helping visualize what's going on. So I strongly suggest folks check out that video. Now, what are we talking about when we say dilation? A dilation is a transformation that can enlarge or reduce the image. Now, this can be done about any point. We are going to focus, just like we did with rotation, we're going to focus on the entire coordinate plane being our image. Now, there might be a segment or a triangle or a quadrilateral on the coordinate plane, but we're going to reduce or enlarge the entire figure as if the origin was the center of our picture. So we're not just going to make that triangle bigger or smaller. We're going to make the entire coordinate plane appear bigger or smaller. And what I mean by that is, if we took a triangle that was 4 units tall and cut it in half, well, now it's 2 units tall. And that's going to happen. But if we take a triangle that is 6 units from the center and we cut it in half, now it's 3 units from the center, meaning the origin. So as we make things bigger or smaller, we're also going to make their distance from the center of the image, the origin, bigger or smaller. And you'll see that as we go forward. Okay, so we are going to treat the center point as the origin. And that's what we're talking about. We're also going to talk about this thing called a scale factor. How much are we making it? Are we making it 2 times bigger? That's a scale factor of 2. Are we making it 1/3 the size? That's a scale factor of 1/3. So we're not dividing by 3, we're multiplying by 1/3. Factor means multiplying. So we have to use the correct terminology. Scale factor, we're multiplying by a factor. That is the definition. We're not changing the shape. All the angles stay the same. We're just creating an image that is bigger or smaller. And for our purposes here, farther away or closer to the origin of the coordinate plane. So some basic terminology, we have a reduction of getting smaller and an enlargement getting bigger. Now these are proportional. If we double the width, we have to double the height. If we cut the width by 1/5, then we have to cut the height by 1/5. We can't just do it in one dimension. A coordinate plane is 2-dimensional, so we have to do it in both dimensions. And as we just discussed, scale factor. Now, a reduction and an enlargement, they are reciprocals of each other. Making it 2 times bigger is a scale factor of 2. Making it half the size is a scale factor of 1/2. So they are reciprocals of each other. So we have to know direction. Are we enlarging or are we reducing in order to get the scale factor correct? Some cases we'll be given the scale factor. In some cases, we have to figure out the scale factor. And here's our rule for dilations. The rule is probably among the most simple. All we're doing is multiplying everything by the scale factor. All our x's, all our y's. We have one scale factor to use for everything. We just have to identify, is it getting bigger or smaller? So here's what we're talking about. If you look at this triangle, again, keep in mind prime notation. So we have to identify what's happening here. An enlargement is a scale factor bigger than 1. A reduction is a scale factor smaller than 1, less than 1, between 1 and 0. So again, 1 is an exact copy, enlargement is a scale factor greater than 1, and a reduction is a scale factor between 0 and 1. So to find scale factor, we can have a simple formula that basically says new over old. So if we look at this example, the new length, CP prime, is 25. The old length of the segment, CP, is 20. Well, that gives us a scale factor of 5/4. That is an enlargement. The triangle got bigger. If we flip it upside down, that would be a reduction from P prime to P. So we have to know which is before the change and which is after. Remember, prime tells us after the change. In this case, the change was a dilation. So we always have to know starting and ending. Let's take a look at it. And let's start with graphing the original, as we always do. A is -3, 1. B is at -4, -1. And C is at -2, -1. So we have our original starting triangle. Now, look at our scale factor. Our scale factor is greater than 1. So this is an enlargement. And we're going to treat the origin as the center of the graph. So watch what I'm going to do. Well, basically what we're going to do is we're going to make everything bigger. We're going to treat the origin as the center of the graph. Our triangle is going to get bigger, but the distance from the center of the picture to the triangle is going to get bigger. Our rule says multiply everything by the scale factor. So A prime, we're multiplying everything by 2. So we get -6, 2. B prime, -8, -2. And C prime, we get -4, -2. So let's look at our new triangle. A prime is at -6, 2. B prime is at -8, -2. And C prime is at -4, -2. And here we can see our new triangle after the dilation. Our triangle is twice as tall. It was 2 units tall. Now it's 4 units tall. But it's also farther away from the origin. Our old triangle, even if you look at point A, it's 3 to the left, 1 up. Now it's 6 to the left, 2 up. Twice as far in both X and Y directions. So we enlarged the image, treating the origin as the center of the image. That's what's happening here. Let's try another one. Look at our scale factor here. It's 1/5. So we're expecting a reduction. Again, we're going to graph the original. In this case, it's a quadrilateral. -10, 0. -5, 0. And of course, we should label our points, so that's P and Q. R is at 0, 5, and S is at negative 5, 5. So we have a parallelogram here. Our scale factor is 1/5. We're going to multiply every number by 1/5. So P prime, negative 10 times 1/5 is negative 2, and 0 times 1/5 is 0. For Q prime, negative 5 times 1/5 is negative 1, and of course 0. And we're just going to multiply these out. 5 times 1/5 is 1. For S prime, negative 5 times 1/5 is negative 1. Positive 5 times 1/5 is positive 1. And let's graph our points. Negative 2, 0 for P prime. Q prime is at negative 1, 0. R prime is at 0, 1. And S prime is at negative 1, 1. And we can see our new parallelogram, which is much smaller. In fact, it is 1/5 the size. And all of our points are 1/5 the distance to the origin. So R was 5 points up. Now it's R prime is 1 point up, 1/5 of that distance. And that's dilations. The other thing we can do is we can put this into compositions with rotations, reflections, and translations. But again, composition means we do one step at a time. All right, let's pick it up there with a little more practice.